All right, so what we're going to take a look at today here, this is actually the first video of what's going to end up being a series of videos talking about simple harmonic motion, commonly abbreviated as SHM. Simple harmonic motion would include things like a pendulum swinging back and forth, or something like you guys look like or looked at when we messed with the mass on a spring applet, when you had the spring just bouncing up and down, and that nice constant oscillatory motion, actually, as it would be called. We look at this, and people say, usually introduce simple harmonic motion by talking about uniform circular motion. I'm going to talk about this very, very briefly, and then we're going to circle back to that quite a bit. So looking at this, you're going to hear me use many uniform circular motion terminologies, but let's talk about kind of how they're related. So there is a connection between those two, SHM and UCM, but the reason why people really connect those two is simple harmonic motion is typically thought of as one-dimensional uniform circular motion. So let's look at a quick link here, actually. Hopefully this will come up for me. Maybe, maybe not. Ah, delightful. Better late than never. So look at this quick little applet here. We have a ball going just around and around in a circle over and over and over again. Hey, that's moving in 2 dimensions. Well, simple harmonic motion is typically just looked at as one-dimensional circular motion. So you see this ball going just side to side, side to side. That just represents one component. Typically, we look at the X component. It really wouldn't matter if it were the X or Y component, but we look at just this simple harmonic motion as one component of the uniform circular motion. So when we look at a lot of equations and a lot of terminologies, hey, those mirror one another. So moving on, talking about the mirroring of UCM and SHM, we have our terms period and frequency. So period, hopefully you remember, it's just the amount of time it takes to complete one trip around a circular path, to complete one oscillation or revolution. Period is shown by the symbol capital T, by that letter, and that is just simply the amount of time, seconds, it takes to complete one cycle. So one full revolution, one full up and down motion, one swing of a pendulum, etc. So then we have frequency. Well, frequency is the number of revolutions that it completes in 1 second. So in terms of period, we have seconds per cycle. In frequency, we have cycles per second. And I could not tell you why, but people frequently mix these two up. Just remember, period is an amount of time that has to be measured in seconds, so it's seconds per cycle. Frequency is 1/seconds, actually, measured in hertz, and that would be cycles per second. So do not mix those terms up. People do it every year. It doesn't matter if you're in regular physics, AP physics, or you're a freshman. People just always mix those up. So what I did here is threw in some questions. What I'd like you to do is answer those to the best of your ability. Show all your work. This is a formal turned-in assignment. So pause the video now and take some time to complete the question. And another question for you here. You will want to pause the video because I'm not just going to leave dead space for you to work on those. All right, and then relating period and frequency, we just talked about it. We defined those values. Well, guess what? They are the reciprocal of one another. One is seconds per cycle. The other one is cycles per second. So an easy way, if, hey, I give you the period, guess what? If you want to know what the frequency is, just hit that inverse button on your calculator. That just, hey, takes the inverse of whatever that value is, whatever that number is. A big reason why you need to know that relationship, that inverse relationship, is because let's say the AP test, they give you a formula That is the frequency of something. Well, guess what? If you take the inverse of that particular formula, that will give you the period of that. So definitely know, remember, understand period and frequency. They're just the inverse of one another. Another simple problem here. All right, another thing we're going to talk about from uniform circular motion, that would be velocity. And velocity is just, hey, 2 pi r over t. That's for anything moving in a circle. And hey, where does that actually come from? I don't like just always giving you formulas and say, hey, know it. This is a circle. It doesn't look like one, but it is. So hopefully you remember the circumference of a circle is, hey, 2 pi r, that's the worst pi ever. And velocity is just simply displacement, delta x, over time. So if we want to know the the velocity of something, well, the circumference would be how far it moved. So that's where 2 pi r over t, it's just the period, the time it takes for one full cycle. So that's where that formula comes from. And then that period and frequency relationship you see right here, we had velocity is 2 pi r divided by t. Well, that means velocity is also 2 pi r times f, just showing, hey, same formula, just using that inverse relationship. Now, the next problem is going to require a little bit more thought. Actually, it's not, because it's just plug and play from the previous formula. I was just kidding. And another problem. All right, next we want to take a look at a few different terminologies. First one is displacement. Displacement is measured from the equilibrium point. Well, what's equilibrium? Hopefully you remember from forces. Equilibrium is when the net force is 0. So equilibrium on a spring would be, it's just resting position. Now it could have numerous resting positions. It could have a resting position where you have no force or no mass hanging from the spring, or it could just be a spring with a mass hanging on it. Equilibrium is when the net force is 0, and we typically measure everything from the equilibrium position on here. So x equals 0, that's the equilibrium position. And then we have the amplitude. That's something you should know from previous classes, but amplitude is just simply the maximum displacement. And amplitude, you typically see that as a capital A. So you see the amplitude, it is positive, it's the furthest away from that equilibrium position. So we do have positive and negative amplitude, and really that just comes down to what we define as positive, what we define as negative. But amplitude A, you'll see that in a lot of formulas going forward, but that's just the maximum displacement. A cycle would just be one full trip motion around. If you remember from the mass on a spring applet, we actually showed that by looking at sine curves. This would be one full cycle. That would be one full period of motion. Yes, you will be seeing some trig functions, trig graphs like crazy here. And then period and frequency, those terms we talked about before. The other thing I want you to see is the force acting on this block actually changes direction. You look at, as the spring's compressed, that spring is going to use a force moving outward. At equilibrium, that force is 0, and once again that would be the net force. As it's moving to its other amplitude, its other maximum point, that force then changes direction, starts going back inward, goes back to equilibrium, and then the force changes direction once again. So that force is constantly changing throughout that motion. Once again, a problem. All right, and then simple harmonic motion and Hooke's law. You remember Hooke's law talked about the relationship between force and extension on a spring. This K value is the spring constant, and is measured in newtons per meter. So it's actually the amount of force required to stretch that spring 1 meter. A large spring, a large spring constant would be a very stiff spring. A low spring constant would be a very just flexible spring. And then a lot of people get kind of confused by this negative in here. All that negative means is it acts opposition to the way you're pulling. So if you're pulling that spring down, it's a restoring force, so it's going to move back up. Some people don't even put that negative in there, but it always goes against the direction you would be pushing or pulling, so it's a restoring force. That's why that negative is in there. Another big point here, the force is not constant. Obviously, the force varies with how much we are stretching or compressing the spring. So that means the acceleration is not constant. What that means for you is, hopefully you remember from kinematics that, okay, let's go with a position time graph, a velocity time graph, and an acceleration time graph. So this would be xt, vt, and at. And if we look at that, let's see if I can actually change colors here. We always had constant acceleration, so we had a nice parabola for our position. Take the derivative of that, had a nice constant slope, a nice linear equation for velocity, and then acceleration was constant. So that made life really, really easy. Well, guess what? Our forces are no longer constant, so things are going to become slightly more complicated. All right, the last slide actually, just going back and talking more about SHM here. The maximum force on the mass is always when it is at an amplitude. So the max force would be either at its positive amplitude or negative amplitude. And the minimum force, actually zero force, is going to be when the spring is not stretched at all. So when it's gone back to equilibrium. And then just two more questions for you here, number 7 and number 8. So that concludes our very brief introduction to simple harmonic motion. We'll get into a little bit of calculus and things in a little more in-depth manner, and talking about graphs in the next video. So hopefully you didn't find this to be too daunting of a task.